Picture the modern industrial world for a second. Just close your eyes and imagine like the sheer scale of the engineering around you.
Right, it's just massive.
Yeah, massive cargo ships cutting through oceans, high-speed rail lines connecting continents, deep-sea oil rigs drilling miles into the ocean floor under, thousands of pounds of pressure.
An incredible amount of force, yeah.
Exactly. Now, I want you to imagine all of that grinding to a violent, screeching halt. Picture the catastrophic friction, the heat, the deafening sound of bare metal tearing against bare metal.
Oh, it would be an absolute nightmare.
It really would. So what actually stands between our modern heavy-duty infrastructure and total mechanical failure? You might think it's, I don't know, advanced metallurgy or titanium alloys.
That's what most people think, right?
Right. But the answer is actually something as seemingly simple yet incredibly complex as a single red blob of grease.
It's literally the invisible bottleneck of modern engineering. I mean, we can design engines to run hotter and gears to turn faster, but without the chemistry that separates those moving metal surfaces, well, the friction would literally tear our machines apart from the inside out in a matter of minutes.
Welcome to the deep dive. Today, we're looking at a single piece of source material that illustrates this perfectly. It's a technical data sheet, a TDS for Jet-Lube's ALCO-EP-73 PLUS Extreme Service Multipurpose Grease.
And it's quite a document.
It is. When you look at this document, the visual anchor at the very top sets the mood instantly. It's this bold, italicized, bright orange Jet-Lube logo. It just looks strictly industrial.
That aesthetic is very intentional. This isn't the generic lubricant you buy at the local hardware store to, fix a squeaky door hinge.
Right, not your everyday spray can.
Exactly. A document like this serves as a highly specific chemical blueprint. It's designed to prove to engineers that this substance will survive in some of the most hostile environments on the planet.
And our mission today is to decode this really dense technical document. We are going to translate this raw industrial data into a real understanding of the extreme chemistry that keeps the world running.
I'm ready.
Okay, let's unpack this. Let's start with the physical architecture of ALCO-EP-73 PLUS. What exactly are we looking at when we observe this red substance?
Well, what's fascinating here is how the datasheet breaks down the two fundamental components of any industrial grease.
Right.
It lists the thickener as an aluminum complex base and the fluid type as lubricating oil. It's critical to understand that grease isn't just, a really thick oil. It's actually a two-part delivery system.
I was trying to visualize the relationship between those two parts while reading it. Is it helpful to think of grease like a chemical sponge?
A sponge.
Yeah, like the aluminum complex is the physical sponge giving it a shape, and the lubricating oil is the water trapped inside doing the actual work.
That's a good starting point, yeah, but you have to look at the mechanism a bit differently than just a passive kitchen sponge.
Okay, how so?
An aluminum complex thickener forms these long, microscopic fibrous molecular chains. And these chains intertwine into a three-dimensional lattice.
Oh, a lattice.
Right. It chemically binds the oil, trapping those oil molecules in the microscopic spaces between the fibers. So it holds the oil in suspension until pressure or movement forces it to release the fluid.
That makes a lot of sense, actually, and it helps decode the consistency ratings here on the sheet.
The NLGI grade.
Yeah. The document gives it an NLGI grade of 2, and it notes a specific gravity of 0.91 alongside a density of 7.6 pounds per gallon. So it's slightly lighter than water, but it clearly has some physical heft to it.
Yeah, the NLGI grade 2 is pretty much the industry standard for general-purpose heavy machinery grease.
What does that look like in real life?
To give you a real-world equivalent, grade 2 is roughly the consistency of smooth peanut butter.
Oh, wow, okay.
Yeah, and the sheet backs that up with a penetration rating of 265 to 295 at 77 degrees Fahrenheit, which is measured under the ASTM D-217 standard.
Wait, that penetration test involves dropping a weighted cone into the grease, right?
Exactly.
And the deeper the cone sinks, the higher the number, meaning a softer grease.
Precisely. By engineering it to hit that 265 to 295 window, they ensure the lattice structure is firm enough to stay exactly where a mechanic applies it.
So it won't just ooze away.
Right. It won't drip out of a vertical gear housing. But when the gears actually engage, the shear force temporarily breaks down that lattice, releasing the oil to lubricate the metal.
And then what happens when it stops?
When the machine stops, the lattice just reforms.
That is wild. So for you listening, Think about that the next time you see heavy machinery moving smoothly. You are witnessing this microscopic lattice being squeezed by tons of steel, bleeding out a microscopic layer of oil, and then pulling it right back into suspension. It's like a completely dynamic cycle.
It is a constant mechanical and chemical cycle. But, that cycle generates friction, and friction generates heat.
Which brings us to the thermal limits, because the numbers in this data sheet require some serious scrutiny, honestly.
They are definitely extreme.
Yeah, it claims an operating range from negative 25 degrees Fahrenheit, which is negative 32 Celsius, all the way up to 450 degrees Fahrenheit, or 232 Celsius. But I have to push back on the margins here.
Okay, what stands out to you?
Well, wait, the maximum operating temp is listed at 450 degrees Fahrenheit, but right below that, the flash point, where it can temporarily ignite, is only listed as greater than 430 degrees Fahrenheit.
Right, the flash point.
Isn't that an incredibly tight margin for error if things get too hot? Like, if your operating temp is 450, but your flash point is 430, aren't you routinely operating a machine inside a window where its lubricant could literally catch fire?
It sounds alarming, sure, but if we connect this to the bigger picture of industrial thermodynamics, the margin's actually built around different environmental conditions.
Okay, walk me through that.
The operating temperature of 450 degrees is the bulk temperature the grease can sustain while remaining chemically intact in the machine.
Right.
The flash point, the greater than 430 degrees, refers specifically to the temperature at which the base oil gives off enough vapor to momentarily flash if an external spark or open flame is introduced right above it.
Oh, so it's not spontaneously combusting at 430. It's just off-gassing vapor.
Correct. Without an ignition source, it just won't burn at 430. Spontaneous combustion is actually measured by the autoignition point, which the data sheet calculates at well over 500 degrees Fahrenheit.
Okay, that feels significantly less terrifying.
Yeah, it's a very safe margin in practice.
And speaking of 500 degrees, the dropping point is also listed at greater than 500 degrees Fahrenheit. The dropping point is the moment that aluminum complex lattice we talked about finally melts, right?
It is the point of total structural failure. The fibers literally untangle.
Wow.
Yeah, the oil entirely separates from the thickener and drops out as a pure liquid. Once you hit the dropping point, you no longer have grease. You just have a puddle of hot oil and a useless soap residue.
So pushing that dropping point past 500 degrees ensures that even at the maximum operating limit of 450, the lattice maintains its integrity.
Exactly. It keeps the grease acting like grease.
We also need to talk about the fluid trapped inside that lattice. The data sheet lists a base oil viscosity of 90 to 110 centistokes at 40 degrees Celsius. I assume centistokes measure how thick the fluid itself is, but I can't really visualize what 100 centistokes looks like.
A centistoke is a unit of kinematic viscosity. Basically, it's just how resistant a fluid is to flowing.
Yeah.
For a real-world comparison, 100 centistokes is roughly the consistency of an SAE 30-weight motor oil sitting at room temperature.
Okay, so it's fairly fluid, but it has some body to it. It's not like water.
Right, and that specific viscosity range is absolutely crucial.
Why is that?
As temperature drops down to negative 25 Fahrenheit, oil naturally thickens. If the base oil were too thick to begin with, it would turn into a solid block of sludge in freezing weather.
And the machine couldn't move.
Exactly. The machine would expend massive amounts of energy just trying to churn the frozen grease. Conversely, at 450 degrees, oil thins out.
Right, heat makes it runny.
If it starts too thin, high heat will turn it into water, and it won't provide a protective film between the metals. So 90 to 110 centistokes is the engineered sweet spot for this massive thermal swing.
That makes perfect sense, but dealing with temperature is only half the battle. Here's where it gets really interesting.
Oh yeah, the additives.
Because a subsea rig or a high-speed engine doesn't just deal with heat, it deals with water, rust, and extreme physical loads. The data sheet points to its additive package, stating ALCO-EP-73 PLUS contains a highly synergistic blend of EPA, which is extreme pressure and anti-wear and RNO, rust, and oxidation inhibitors.
Right, that's a very robust package.
It also specifically notes polymer additives for inherent water resistance.
The word synergistic there means these chemicals are specifically chosen because they actually amplify each other's effects.
Oh, interesting.
Let's look at those polymers. When you add specific polymer molecules to the aluminum complex lattice, they act like long, sticky strings that weave through the structure, pulling it tighter together.
Like reinforcing the sponge?
Yes, and they increase the surface tension, creating a highly hydrophobic barrier. Water molecules simply cannot penetrate the lattice. They just beat up and sheet off.
That makes sense. But the EPA additives, the extreme pressure and anti-wear package, caught my attention because the sheet specifically calls them non-plating and organic.
That's a huge selling point.
Yeah, it says this makes the grease suitable where tolerances are low and speeds are high.
That is a critical distinction in modern engineering. You see, many traditional extreme pressure additives are reactive metals, like zinc or molybdenum.
Okay.
Under high heat and pressure, they undergo a chemical reaction with the steel gears, forming a sacrificial metallic layer. They literally plate the metal.
I was trying to figure out a way to conceptualize why you wouldn't want that, because plating additives seem like repairing a pothole-filled road by pouring layers of asphalt over it. Sure. It protects the base of the road, but eventually the road gets higher and thicker until a truck can't fit under an overpass anymore.
That is a brilliant analogy.
Right. But non-plating organic additives, on the other hand, seem more like an electromagnetic force field that hovers just above the road. It keeps the tires from ever touching the asphalt without adding any permanent physical bulk to the street itself.
That is a much more accurate way to look at it. If you have an old, slow-moving tractor, plating is fine.
Because there's plenty of room between the gears.
Exactly. But think about modern high-speed rail lines or precision turbines. You have mathematically perfect, microscopic gaps between the moving parts.
Oh, so if it builds up?
If your grease is constantly depositing a new metallic layer onto the gears, it's effectively changing the physical dimensions of the machine. The gears will bind.
That would be a disaster.
It would. Organic non-plating additives create a temporary, durable film that handles the pressure and then just dissipates without leaving a permanent deposit. It protects the metal without changing its shape.
That is incredible engineering.
Yeah.
And you want to talk about chemical stability. The oxidation resistance test really blew my mind.
The ASTM D-942 test.
Yes. It's measured as less than a 5.0 psi drop over 100 hours.
Better known as the bomb oxidation test.
Yeah.
It's a fascinating metric for how well those RNO rest and oxidation inhibitors actually work.
Right. They put a sample of the grease into a sealed steel chamber, which is the bomb, and fill it with pure oxygen under high pressure.
Correct.
If the grease is chemically reactive and prone to oxidizing, it will physically consume the oxygen gas from the air, which causes the pressure inside the chamber to drop.
Which means it's breaking down.
Exactly. So a pressure drop of less than 5 psi over a full 100 hours of exposure means this grease is essentially ignoring the oxygen. It refuses to break down.
It's highly inert. And they verify that lack of reactivity with the copper strip corrosion test, which the sheet lists as a 1A rating.
I really wanted to ask about that. Why copper? Heavy industrial machinery and deep-sea rigs are made of steel or titanium, not copper.
It's a great question. Copper is incredibly soft and highly reactive, particularly to sulfur.
And sulfur is in the grease.
Sulfur is a very common element in extreme pressure additives. If a lubricant has unstable or highly corrosive additives, it will rapidly etch, pit, or turn a copper strip black.
Oh, I see.
In the test, they bury a polished copper strip in the hot grease. A rating of 1A is the absolute best possible score on the scale.
Meaning it didn't react at all?
It means the strip comes out looking freshly polished. If the grease is gentle enough not to tarnish hot copper, engineers know it won't corrode their highly sensitive steel alloys over time.
Okay, so we've established the mechanics. We have an aluminum lattice holding 100 centistoke oil reinforced with hydrophobic polymers and a non-plating force field.
Very capable substance.
Now we have to subject it to the real world. The data sheet explicitly targets hostile environments. It points out that it exceeds the military specification, MILG 19458BSH.
That's a rigorous spec.
And it is ideally suited for subsea applications. Plus, it highlights its use on squnch and RL4 and other similar oilfield connections.
When a product explicitly targets subsea environments, you have to consider the physical realities of the ocean floor. You are dealing with freezing temperatures, highly corrosive salt water, and massive crushing pressure from miles of ocean depth.
I actually had to look up what a squnch connection is.
Oh, did you?
I did. It turns out a squnch joint is a threadless mechanical connection used in subsea drilling. Instead of screwing massive pipes together, they essentially drop one massive steel pipe into another, and they lock together under immense weight.
That's exactly right.
You are putting grease onto a metal joint that is going to be slammed together by thousands of pounds of steel underwater.
This raises an important question about the physical limits of the grease under that kind of crushing weight.
Like, when does it fail?
Exactly. How much pressure does it take to push the grease entirely out of the way and let the metals destroy each other?
Well, the datasheet answers that with the shell 4-ball test results. The ASTM D-2596 standard.
The ultimate stress test.
The numbers here are intense. I mean, it lists a weld point of 315 kilograms, a load wear index of 38, and a wear scar diameter of 0.7 millimeters.
The shell 4-ball test is basically a brutal piece of engineering theater. It's used to find the absolute breaking point of a lubricant.
How does it work?
They take 3 steel balls, lock them together in a triangle, and press a 4th steel ball down into the center groove while spinning it at high speeds. Then they just keep increasing the downward weight.
So they are actively trying to destroy the fluid film.
Yes. They force the organic non-plating additives to take the brunt of the abuse. The KGF stands for kilogram force.
Okay.
Now, 315 kilograms, which is about 694 pounds, might not sound like a lot of weight when we were talking about heavy machinery, but you have to remember the geometry of the test.
Right, because a spinning sphere pressing into 3 stationary spheres means the actual contact area is incredibly tiny.
Exactly. It's microscopic. So that 315 kilogram of is concentrated entirely on a surface area the size of a pinhead.
Oh, wow. So the pressure is immense.
The contact pressure is astronomically high. A weld point of 315 kilogram F means they had to apply that immense concentrated crushing force before the additive force field finally collapsed.
And then the metal superheats.
Yes, the metal superheats from friction, and the 4 steel balls literally weld themselves into a single solid chunk.
That is an astonishing amount of pressure resistance for something that is ultimately mostly oil and soap.
It really is.
And the wear scar diameter of 0.7. That means the physical damage to the balls under typical testing loads leading up to the weld point was less than a millimeter wide.
That 0.7 millimeter scar is the physical proof that the organic additives are doing their job. Even when subjected to violent spinning and crushing pressure, the chemical barrier prevents all but a microscopic fraction of a millimeter of physical damage to the steel.
So what does this all mean? Let's bring this full circle for you, the listener. What we've uncovered today is that Jet-Lube's ALCO-EP-73 PLUS isn't just grease.
Not at all.
When you hear that word, you probably picture like the black grime on a bicycle chain, but this is a meticulously calculated chemical emulsion. It is an advanced delivery system.
A very advanced system.
It's an aluminum lattice suspending carefully measured oil, reinforced with hydrophobic polymers, and shielded by non-plating organics. It's designed to survive 500-degree heat, extreme subsea saltwater exposure, and the kind of microscopic, localized pressure that would literally weld lesser metals together.
It forces you to rethink how you view industrial maintenance entirely, doesn't it?
It really does.
We look at massive steel rigs and marvel at the mechanical engineering. But the mechanical engineering only functions because of the chemical engineering hiding in plain sight, contained within a red paste.
It's incredible. And I want to leave you with one final provocative thought to mull over today as you look at the infrastructure around you. As human engineering pushes further into the unknown, as we build deeper ocean rigs, design high-speed trains with mathematically flawless tolerances, and demand machinery that operates faster and hotter than ever before, the ultimate bottleneck of our technological progress isn't actually the strength of the steel.
It really isn't.
It isn't the titanium we forge. The true frontier of extreme engineering isn't mechanical at all, it's chemical. It is the invisible microscopic chemistry of the grease that sits between those massive metal plates. Because, as we established right at the beginning, without that single red blob of grease acting as a shield, the entire modern world grinds to a violent, screaming halt.